Welcome to the deep dive. Ever just look up at the night sky and really think about galaxies? I mean, these huge swirling things. They're not static, right? They're moving. Today, we're diving into how galaxies actually spin and what that spin tells us about what's really going on inside them, maybe the stuff we can't even see. Our mission, really, is to explore one specific study, a truly foundational piece of work that basically rewrote the book on galactic motion.
Yeah, absolutely. We're talking about the 1970 spectroscopic study of the Andromeda Nebula, that's M31 by Vera Rubin and Kent Ford. And you really can't overstate its importance. It was let's say, a real game changer in astronomy. It pushed back hard against what people thought they knew. M31 itself, Andromeda, it was perfect for this. It appears so large in our sky, because it's relatively close. That let them map its rotation in, incredible detail for the time.
Okay, right. So let's unpack this a bit. How do you actually measure the spin of a whole galaxy? It sounds impossible. It's not like you can, I don't know, attach a cosmic speedometer or something. What tools, what techniques did Rubin and Ford use back then? How did they see it spin?
It really comes down to the physics of light. Their main method was spectroscopy. They looked very closely at specific patches within Andromeda called HII regions. Think of these as giant clouds of glowing hydrogen gas, super bright because lots of new stars are forming inside them, like cosmic beacons. These beacons act as tracers. They move along with the galaxy's gas and dust, so if you can track them.
I'll track the galaxy's movement.
Exactly. And to track the movement, they measured the Doppler shift. You know the effect, right? Like an ambulance siren changing pitch.
Yeah, higher pitch coming towards you, lower going away.
Same idea with light. If an HI region is moving towards us, its light shifts slightly blue. Away from us, it shifts slightly red. They focused on specific wavelengths, specific emission lines, mostly H-alpha and lines from nitrogen together, and measured those tiny shifts very precisely. That gave them the radial velocity, the speed towards or away from us.
Wow.
And for the tech, they were really pushing the limits for 1970. They used something called a DTM image tube spectrograph. It was mounted on the big 72-inch telescope at Lowell Observatory. Pretty cutting-edge stuff. It allowed them to capture faint light and get the spectral details they needed.
So using light shifts to measure speed, ingenious, really. Okay, they had the method, they had the tech. What did they actually find when they started gathering data from these HII regions in Andromeda?
Well, they gathered a good amount of data. They studied 67 of these HI regions, spread across a really wide area of M31. We're talking from about 3 kiloparsecs, that's roughly 10,000 light years out from the center, all the way out to 24 kiloparsecs, so a huge range.
Okay.
And right near the center, say inside that 3 kiloparsec mark, they saw the rotational speed climb really fast. It actually peaked at about 225 kilometers per second, surprisingly close to the nucleus, only about 400 parsecs out. So yeah, a really fast spin right near the core.
Whoa, 225 kilometers a second. That's fast. Right at the core. So
Yeah.
that's where it gets really interesting, right? What happened next? As they looked a bit further out, but still kind of close to the middle, did it just keep going up?
You'd think maybe it would or level off slowly, but no, that's the first surprise. After hitting that peak speed, the velocity actually dropped. It fell into quite a deep minimum, a dip, around 2 kiloparsecs out from the nucleus. An unexpected slowdown after that initial rapid spin-up.
Huh. A burst, then a dip. Okay, that's already not quite what you'd maybe intuitively expect. So now the big question, what happened way out? Beyond that dip, out towards the edge of their measurements at 24 kiloparsecs, did things finally start behaving, predictably?
And this is the finding that really shook things up. The simple answer is no, it didn't behave as expected. Not at all. See, the prevailing idea, based on how gravity works in, say, our solar system, was that speeds should decrease further out. Mercury zips around the sun way faster than Neptune does because most of the mass is concentrated in the sun. But Rubin and Ford found the opposite, or rather something completely different. The rotational velocities just stayed high. Remarkably high and basically flat, or maybe even slightly increasing all the way out to 24 kiloparsecs.
Flat, like no decrease at all.
Pretty much flat. The optical velocity they measured way out at 24 kilopc was around 270 kilometers per second. And crucially, this matched up really well with separate measurements made using radio telescopes, looking at the 21-centimeter line from neutral hydrogen gas. So independent confirmation. And that plot of velocity versus distance, that's what astronomers call a rotation curve. And M31's rotation curve, according to Rubin and Ford, was undeniably very flat, or nearly flat, in its outer parts. A huge discovery.
Okay, hold on. Flat rotation curve. Things not slowing down way out there. That feels wrong somehow. Based on where the stars and bright gas are,
Hmm?
doesn't that just completely mess with our ideas about where the mass in a galaxy is supposed to be? Like, there must be something else going on.
Exactly. You've hit the nail on the head. That flat rotation curve has profound implications for mass distribution. For things to be moving that fast, that far out, gravity needs a much stronger pull than what you'd calculate just from the visible stars and gas clouds. It means there has to be a huge amount of mass out there at large distances from the center, mass that we can't see, mass that isn't emitting light like stars do.
So, invisible mass, dark matter.
Precisely. This was some of the most compelling evidence for what we now call dark matter. This unseen stuff must make up a significant portion of the galaxy's total mass, extending far out into a kind of halo. It implies the density of this invisible component, decreases much more slowly with distance than the visible matter does. The glowing part of the galaxy is just, well, the tip of the iceberg.
Okay, so based on these speeds, how much mass do they estimate Andromeda actually has?
Their calculations, based on that flat rotation curve out to 24 kiloparsecs, suggested a total mass of around 1.8 to 1.9 times 10 to the 11th solar masses. So almost 200 billion times the mass of our sun. And remember, earlier models, like those from Brandt or Schmidt, they predicted velocities would drop off significantly further out. So Rubin and Ford's results were a direct contradiction, which made them so impactful it forced people to confront this discrepancy.
Okay, but given how weird this was, how revolutionary, could there be another explanation? Could the velocities they measured not be purely rotational? Like maybe the outer parts of the galaxy were expanding or contracting, or had other weird motions that just looked like fast rotation?
That's a really important check to make. Could it be non-circular motions fooling them? And they did look into that. They specifically analyzed their data for signs of significant expansion, contraction, or other non-circular movements. Their conclusion, they found no evidence for anything substantial like that. The velocities they measured seemed to genuinely represent the rotation of the galaxy.
Right, so the measurements were solid, the rotation was that fast.
Yes, which makes the conclusion about the unseen mass much, much stronger. It wasn't some observational artifact or peculiar motion. It seemed to be a fundamental property of how Andromeda and likely other spiral galaxies are put together.
Wow, what an incredible piece of detective work. This study by Rubin and Ford, it wasn't just about Andromeda's spin, was it? It fundamentally shifted our view of galaxies, of mass, well, of the universe's inventory.
Absolutely, it was a paradigm shift. The key takeaway, the thing that still resonates so strongly today, is that those high speeds way out in the galactic suburbs, they were undeniable proof that galaxies are dominated by far more mass than we can see. This unobserved component, this dark matter, is essential. It provides the extra gravity needed to hold these rapidly spinning systems together. Without it, they'd fly apart.
It really opens up a whole new perspective.
It certainly did. It launched a whole field of research into dark matter that's still incredibly active today.
And it makes you think, doesn't it? If this one study, looking closely at the light from Andromeda nearly 50 years ago, revealed this vast invisible component shaping galaxies, what other fundamental forces or components might still be out there, completely unseen by us right now, subtly shaping the cosmos, just waiting for the next breakthrough, the next Vera Rubin, to bring them into the light?